Right, so now what we're going to do is there's still three-dimensional things, like with the shapes that were popping up out of the paper. But instead, the way of like shapes, instead of shapes, the way we're getting our three-dimensional object is you're going to take this, two-dimensional thing that's going to be drawn on your paper and spin it. So you're going to rotate around an axis. So what that means is all of your slices are going to be circles, because when you spin, it's going to make a circle. So what is the area formula for a circle? A whole circle. Pi r squared. We're used to doing semicircles, but pi r squared, a whole circle. And so that's what you have in here. It's going to be pi r squared, and then your integral from wherever to wherever. If you rotate around a horizontal axis of revolution, like the x-axis, so if you have something like this and you spin around, it's going to be a dx problem. Everything will make sense. It'll be upper minus lower, life is good. If it's a vertical axis of rotation, like the y-axis, it's going to be a dy problem. So if you spin around a vertical axis, it'll be dy. I usually just say if it's around x, it's dx. If it's around y, it's dy. If it got shifted somewhere else, it's the same idea. Okay, so we're still going to start by drawing these. Find the volume of the solid of revolution obtained by revolving the plane region. You know, they're all going to start by saying that. Y equals square root of x. What are some points I can put on for that? 0, 0, 1, 1, close, 4, 2. All right, the line x equals 4, so vertical line at 4. Oh, and I skipped this one, and the x-axis. So here's your shape, and you can take or leave my advice, but here's the advice I give for these ones. Erase all of these little tails. Like erase all of the part that is outside of just that shape, because we now want to take that shape and spin it. And if you have all those extra lines everywhere, it can look like overwhelming. So I always just say erase those. So just write with pencil and erase them. We are spinning around the x-axis. So I call it the ghost shape. What you want to do is draw a reflection of this over the x-axis. This is your ghost shape. And you're going to have a little bit of an imagination here. We're taking this and we're spinning it around the x-axis. So you have to imagine this as a three-dimensional object. Like this is coming up out of the paper and spinning around. It's a three-dimensional object. What it would look like is kind of like a cereal bowl that you couldn't put any cereal in because it's solid the whole way through. Do you get what I'm saying? There's not like an opening in it. It's just solid the whole way through. Or like a top that you could spin. You know what I'm talking about? Are you envisioning it with me? Like, okay. Or like a vase that you couldn't put any flowers in because it's solid the whole way through. Okay. So integral from where to where? It's going to be a dx problem because we're spinning around the x-axis. So look at your x numbers. Integral from where to where? 0 to 4. And what goes in there is pi r squared. Now we usually put pi out front, kind of like evict that. In fact, you could do the whole problem and then just stick pi in your answer. Pi r squared. So your radius is this, and it's going to be upper graph minus lower graph. So what's our upper graph? Square root of x. And your lower graph is the axis, which is 0. So it's square root of x minus 0, which would just be square root of x and then dx. So pi r squared, don't forget the squared. In fact, usually, I don't know why I didn't do it this time, but usually I set it up blank, like I'll put pi blank squared dx. And then, so what's going to happen to that? Yeah, it'll just be x, and then we can do the antiderivative. So what's your antiderivative of like just x? Yeah, 1/2 x squared such that 0 to 4, and then upper boundary minus lower boundary. The lower boundary is just going to be 0, so you don't even really need to worry about that. If you plug in 4 squared, 16, half of that, 8, so 8 pi. Units cubed. We don't really use units for these, but it's a three-dimensional thing. So like if this was inches, it would be like cubic inches for that like three-dimensional thing. Let's try another one. Find the volume of the solid generated by revolving the region bounded by, all right, y equals x cubed. What are some points we can get on our graph for that? 0, 0, What else? 1, 1. -1, -1. And then you would have 2, 8, but that's going to go off the grid. It would be like up here. And so it's going to be this like wiggly thing. And then the y-axis, so just the y-axis, and then the line y equals 3. So that's right here. So here's your shape. And again, what I usually recommend for this is erase all those little tails around the outside of it. You don't have to, but I feel like it helps for you to like see what's going on. And then what are we spinning around? So it's going to be a dy problem. Draw your ghost shape on the other side of the y-axis. It's going to look like this. It's like a Hershey kiss. Like, are you imagining this three-dimensionally? Like, if you flip that upside down, see how it looks kind of like a Hershey kiss? It's like solid the whole way through. So as soon as you realize it's going to be a dy problem, you have to make a full commitment to the entire thing being backwards. So you have to go back to this equation and rearrange it. So how would we solve this for x? Cube root. So it'll be cube root of y equals x. And again, I've just found over the years that if you circle that, that helps for whatever reason, like reminding you what to put in your integral. So it's going to be pi r squared dy. I don't know why I didn't do that on the first one. That's usually how I recommend setting it up. Do pi r squared and then dx or dy at the end. Because if you set it up blank, then you can just go fill it in. This is like your framework of the problem. So boundaries, you need y values because it's a dy problem. So look at your y-axis. It'll be from where to where? 0 to 3. And then this is your radius. Instead of upper minus lower, now it's right graph minus left graph. So your right graph is that cube root of y. Your left graph is the axis, which is 0. So it's just going to be cube root of y. Now I'm going to rewrite that before we do the antiderivative. How can I rewrite this with a fraction exponent? I know you're like, oh, geez, it's either 2/3 or 3/2. Which way is it going to go? Y to the what? 2/3. Whatever kind of root it is, that goes in the denominator. And then we will do the antiderivative. So pi is just still hanging out there out front. And again, you can do the whole problem without pi and then just stick it in at the end. You have to add 1 to the power. This is fun with fractions here. If you add 1 to this, 1 plus 2/3. 5/3, good. What goes out front then? 3/5. Such that 0 to 3. And so it's upper boundary minus lower boundary. You don't really need to worry about the lower boundary though, because it's 0. So we're just going to plug in 3. And I strongly recommend just leaving these alone. There's nothing you can do to that to make that look any nicer. Like the first one came out to 8 pi. That was kind of nice. But if you can't do anything to it, just walk away. I would in that case. If you wrote it back, it would just look like this. It would be pi and then 3/5. What would that be? Cube root of 3 to the 5th. It just doesn't really make it any better. We'll do one more together and then I'm going to give you one to try. Find the volume of a solid generated by revolving the first quadrant region. All right, so just the part in quadrant 1. Bounded by, all right, we need some points to plot on here. What can give me 1 point where we can start? All right, 0, 4, perfect. Going to be an upside down parabola. 1, 3. And you would also get -1, 3. I'm not going to bother with that though, because it said to stay in quadrant 1. And then 2, 0. So it's going to just be this. And if you want to even just go ahead and copy that over for part B, it's a part A and a part B. So we're using the same shape for both of them? So for letter A, we're going to spin around the x-axis. So draw a ghost shape on the other side of the x-axis and try to imagine this as a three-dimensional thing. I feel like it looks kind of like a pitcher's mound, only like very exaggerated. Do you know what I'm talking about? Like a dome kind of thing. I like to try and get everyone to engage their imagination because when I teach this unit, it mostly happens with AB. People are like, Ms. Cole, I just memorized how to do the problems. I don't understand anything I actually did, and that makes me sad. So I want you to actually like try to visualize them. So this is going to be pi r squared dx. Set up like the framework of it, and then you can just go back and fill in everything. I feel like when you set up the framework, it calms you down because you're like, oh, it's just all that. I just go fill in the blanks. So what are your boundaries? They have to be x because it's dx. 0 to 2, perfect. And then your radius is upper graph minus lower graph. Again, the lower graph's just the axis, so you kind of don't need to worry about that. So your upper graph just is 4 minus x squared. Now we're going to have to do a tiny bit of algebra before we can do the antiderivative for this one. So one more step before we do the antiderivative. 4 minus x squared squared. I'm just going to write off to the side. What does squared mean? Like when you square something, what does that mean you did? Right, so it's going to be 4 minus x squared times 4 minus x squared. And if you can do that in your head, you don't have to write that, but I just put it off to the side. You have to distribute all that stuff to each other. So 4 times 4, 16. This would give you negative 4x squared. And then these two would give you negative 4x squared. So together, good, negative 8x squared plus x to the 4. Okay, good. That wasn't like pulling teeth. You guys know how to do algebra. I call that FOIL, first, outside, inside, last. Have you ever had a teacher call it that? FOIL? No? Okay, well, it's just distributed. Now we can do the antiderivative. So antiderivative would be what? 16x minus, perfect. Beautiful. Such that 0 to 2, I wrote too big, oopsie. Upper boundary minus lower boundary, but again, typically the lower boundary is 0. If you plug in 0 for all those x's, they're just going to go away. So basically just plug in 2 to the whole thing. It'll be 32 minus 2 cubed would be 8 times 8. Good. So minus 64 thirds plus, do you know 2 to the 5th? Is that one that you know or not? 32 and then fifths. So 32 fifths, whatever that is. You don't even need to simplify it down as much as I did. You could just plug in the 2, but I was just trying to talk us through that a little bit. So this one, we're spinning around the y-axis, so it's going to be a dy problem. As soon as you realize it's dy, what should you stop and go back and do? Yeah, go back and rearrange the equation. So I'm just going to write like off to the side here. The equation was y equals 4 minus x squared. What would we do to rearrange that? Minus 4, there we go. Y minus 4 equals negative x squared. Oh, then you have to divide by a negative. So it'll be negative y plus 4 equals x squared. And then square root that. All right, and then usually I circle that. That kind of helps. So setting this up, pi, that is a very bad pi. Pi r squared dy, you want to look at your y-axis. What are your boundaries going to be? 0 to 4, And then in here, it's going to be right graph minus left graph for your radius. Now the left graph is the axis. That's just going to be 0. So your right graph just is this. It looks kind of scary at first, but what's going to happen? Oh, I'm sorry. The square root's going to cancel. Because for a second, it looked like that was going to be an awful thing to do an antiderivative of, but that all just goes away. So what's your antiderivative? Negative 1/2 y plus 4y. Oh, good. The common mistake there is people will put 4x, and I totally get why that happens. Such that 0 to 4, and then we're basically just going to plug in 4. So let's see. 4 squared. 16, half would be 8, but it's negative. So negative 8 plus 16. So actually, what does that boil down to? 8y. Hey, isn't that the same thing that we got for this one?
What?
Oh my gosh. Look at that problem, and then look at this one. What do you notice? It's the same, except it's turned the other way.
Wow.
So for these last two, instead of rotating around the x-axis or the y-axis, we're going to shift the axis of rotation, which just changes how you're going to set it up a little bit. So find the volume of a solid generated by revolving. All right, let's go ahead and graph it. Oh, big red flag here. What does this tell you is probably going to be the case? Yeah, it's going to be like a dy problem, like it's going to be sideways. Let's get some points to plot. It's going to be a parabola. It's just going to be sideways. What's one point we can put on there? Like, where would you start? Oh, you wouldn't go for 0? I would start at 0, 0. But you guys are right. 1, 1 as well. And also 1, negative 1. Good. It's going to be a regular old parabola, like y equals x squared, except sideways. So what's another point we can get? Close. 4, 2. And then also 4, negative 2. It's exactly y equals x squared, but for x equals y squared, it's just going to be sideways. And you're probably like, well, it's not a function. It fails the vertical line test. Again, for these problems, these areas and volumes, we don't care. We just are finding the area and volume of, whatever it is. All right, and then x equals 4. So here's this vertical line at 4. So here's our shape. And again, my suggestion is kind of like erase all the tails around that to kind of like clean it up a little bit. And so it makes it a little trickier to tell if it's dx or dy. Now this one had like a big clue there. When you move the axis of rotation, we're going to rotate around x equals 4. So what I usually do is dot that in. So here's our x equals 4. That's our new axis of rotation. And so just watch me point to this. If we rotated around the y-axis, it would be dy, right? That makes sense. Around the y-axis, dy. It's like we just took the y-axis and scooched it over a little bit. Do you get what I'm saying? It's like we took the y-axis and just moved it over here. So it's going to be a dy problem. Your ghost shape is going to be on this side. So draw like a reflection over that. And so you have to imagine this 3-dimensional object that's being created. It would look like an egg. Like an egg that's solid the whole way through. Are we seeing that? It's a chocolate egg for Christmas. Solid the whole way. Like a Cadbury egg. Do you know those? They're kind of gross, but like gooey inside. All right. So pi r squared dy. And so when you get your boundaries, you want to look at the y-axis. So look at your y-axis. It'll be from where to where? Good, -2 to 2. And your radius is going to be right graph minus left graph. Now, so far, one of them has been 0 for all the other problems because we were going around the axis, but this one is going to actually be right graph minus left graph. So what is the right graph? Yeah, just 4, right? Minus the left graph, which is y squared. Good. Now you would have to do 4 minus y squared squared. So imagine 4 minus y squared, 4 minus y squared. I think it's actually the exact same as the one we did, except y instead of x, isn't it? Yeah, do you see that there? We're gonna do that again, except with y instead of x. So pi integral -2 to 2. If you multiply all of that together, it'll be 16 minus 8y squared plus y to the 4th. And again, I wrote way too big, I'm sorry. And so then that antiderivative is going to be the same as well, right? Except it's y. So when you do the antiderivative, it'll be 16y, good, minus yep, perfect, such that -2 to 2. Now also annoyingly for this one, we can't ignore one of the boundaries. Like one of the boundaries isn't 0, so you're gonna have to actually do upper boundary minus lower boundary. And I'm so sorry, I wrote way too big and it didn't fit on here for me, but I will try to write really small. It's gonna go into the grid, but that's okay. So pi out front, if we plug in 2, that'll be 32 minus 64 thirds plus 32 fifths. So that's the upper boundary. Minus pi, and then we're going to plug in -2. So that'll be -32 plus 64 thirds minus 32 fifths. Now there is some canceling I feel like you could do there. Like if you were to distribute this negative, like you see what I'm saying? Some of that stuff would like go together or cancel out. But at that point, I would just stop. If you don't have to figure it out for multiple choice, I would just not go any further. All right, last one. Find the volume of the solid generated by revolving the region bounded by. All right, y equals -x squared. What are some points I can put on that? It'll be an upside down parabola. 0, 0. All right, what else? Yeah, 1, -1. And so also -1, -1. And then good, 2, -4, -2, -4. And then y equals -1 would be right here. And so you end up with actually this like tiny little shape. All right, so erase all these little tails around the outside of that. And we're going to revolve around y equals -1. So I guess if you wanted to leave that, I always try to dot in the axis I'm revolving around. So we have this tiny little shape. And so your ghost shape is going to be right here. And so I guess it would almost be a sphere, except like squashed a little bit. Are we envisioning that? Like 3-dimensionally, it would like almost be a sphere, but kind of like a sphere someone like crunched a little bit down. But will it be dx or dy? Yeah, it's like you just took the x-axis and scooched it down a little bit. So it'll be dx. So pi r squared dx, just set up the framework of it. That also helps you not forget the pi. You do pi r squared dx, just set it up. So look at your x-axis for the boundaries. That'll be from where to where? -1 to 1. And your radius will be upper graph minus lower graph. This is super tiny in here, but upper graph minus lower graph. I was going to say, let me zoom in, but I don't have a zoom anymore. I just have to move this manually. So which one is the upper graph? Yeah, the -x squared is the upper graph. Oh, good. I thought I was going to have to talk you guys through that. Why is it +1? Yeah, it would be minus the lower graph. So minus -1, which would then be +1. Okay, cool. I thought I was going to have to fight for that one, but you guys got it. All right, so pi integral -1 to 1. We have a little bit of algebra to do before we can do the antiderivative. It's -x squared plus 1 squared. So if you can do it in your head, that's totally cool. If not, just maybe like write it twice off to the side. We're gonna distribute all of that to each other. So what would that get us? Yeah, positive x to the fourth, good. Minus 2x squared plus 1 dx. That's going very smoothly. Okay, good. Usually I have to like fight with everybody on that. All right, then you can do the antiderivative. So that would be 1/5 x to the fifth minus 2/3 x cubed plus x, such that -1 to 1, and then it's upper boundary minus lower boundary. So let's see what we get. If we plug in 1, that'll just be 1/5. Oh, pi out front. 1/5 minus 2/3 plus 1. 1 is easy to deal with. Minus pi, and then do the same thing with -1. So that'll be -1/5, like the exact opposite, right? Plus 2/3 minus 1. And again, you could do some more simplifying down there. I believe that you could if I forced you to, but I'm not trying to torture you, so we'll just go ahead and stop.